Anyway, let's get this party started, shall we? So, build systems. Not exactly the world's most glamorous topic. They're not something that's going to win you any job offers, and they're not someone that's going to get people's attention on your resume. But, so I can understand, this is long, this is complicated, this may not be very immediately useful to what you're doing right now, and it's not exactly fun and flashy. But build systems are one of the most key parts of any software project. You can't write like serious code without a serious build system that can keep up with all the things that you need to do. Managing dependencies, handling weird compiler flags, generating source files, all that kind of thing. You need to be able to be good with build systems in order to handle when you need to do that in your software projects. And I promise, if you can make it through this series of 5 lectures, you'll know more about build systems, about C++ build systems at least, and about 75% of professional software engineers, at least if my Qualcomm experience is any judge. And this is a great way to earn points in a new workplace. If you want a story about that, so when I was at Qualcomm, I know I did an avionics meeting, but I'm going to review it for people who are here. So the build system we had to work with took almost an hour to build the entire OS image and flash it onto the target device. It was so slow. But instead of using that, I spent my first week on the project writing a new build system and an incremental upload tool in CMake that would, instead of rebuilding the entire thing, would just rebuild my application. And this made my incremental builds of my app take about 12 seconds instead of over 30 minutes for even changing one source file. So that meant I could iterate quickly instead of taking ages and ages and ages to create and test new things. People always like, how are you making progress so quickly? Answer, build systems. So before we can really talk about CMake, I just want to do a quick review of how exactly C++ code gets built. Because some of you may already know some of this, but I want to make sure everyone knows about this so that it will make sense once we move on. So first, I wanted to take you guys through manually building a C++ program. So we're going to compile like a little program I made from the some of the moving quadreg stuff we had a while ago. It has 2 parts. We have moving quadreg.h and .cpp that has a little quadratic regression thing, and then we have test regression.cpp, which is a test program for moving quadreg. You may have already seen this code before if you worked with it. I just have it like in its own little repository. It's just a demo for us to work with. So when you build C++ code, there's 2 basic steps, compilation and linking. So in compilation, the compiler goes through the source file and finds all the functions and code you've written in there, and then it turns it into machine code, which is code the processor can execute, which is, of course, binary. You can't work with this code, but the processor can. So this stores it in an object file.o. I know that is the most confusing name ever because there's so many other definitions of the word object in programming. They have nothing to do with object file, but in object file's defense, it was first, like 1970s first. So errors in the source code are detected this time. Then linking is when you take all of your object files and you merge them together into a single program. This actually gives you an executable you can run or a library you can work with, which we'll talk about libraries a little later. So if there's any errors in the complete program, these are detected this time. This is where you get your undefined reference to blah, 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 blah error. That comes at linking stage. How many of you have gotten those errors? Raise your hand at one point or another. Undefined reference errors, Rita? Yeah. Welcome to the club. So I wanted to give you a little, we're going to walk through building this code on the command line. If you haven't done, how many of you have done G++ on the command line before? You can use the raise hand function. All right, good. So so a lot of you have. If you've taken CS 104, then you've done something like this before, but it might have been a while. So anyway, I want you to all open up a terminal to the CMake training exercises section 1 folder in that repository I sent, and they're going to run these commands that I have on here. These should build your executable for you. You can check it out. I'll give you 5 minutes to work on this, and then we'll come back.
Hey, Jamie, I joined a little late. Where can we find this repository?
If you look in avionics announcements, there's a link to it.
Cool, thanks.
If you're watching the YouTube recording of this, I'll put the link in the description.
Also, Jamie, the last subfolder is session 1, not section 1, just for editing.
Oh, whoops! Yeah, session 1. Whoopsies. You need to clone using the HTTPS URL, not the SSH URL, because you don't have SSH keys set up on WSL, and they're a royal pain in the butt to set up. I hate working with Git SSH keys.
All right, got it. Yeah.
Cool.
Wait, Jamie, are you going to explain what each of these things do, like
Yep.
-C and -no? Okay.
I'm going to explain after this. Promise. Just wanted you to have the experience of doing it before. But I guess I can give a little summary now, which is, so number 3, so the 2 G++ commands, these are compiling commands. These are all compiling. So with these, you will run up the command. You will they take .cpp files and then they output .o files. That should be enough. You know they're compiling. And then this one is a linker command.
So on the, I guess on the Linux terminal, I'm trying to figure out like what exactly you mean by terminal. Is that like the thing that pops up when you have the username and password?
Yep. So you installed WSL, right?
Yeah.
So open up Ubuntu, right?
Okay.
That's what I mean by terminal. And then did you clone the repository?
Yeah.
Yeah, so just cd into there and then run those commands.
So is a linking command sort of like what we achieve using a Makefile, but instead of doing that, we're actually doing it in command line?
Yep. If you've done Makefiles, these are just taking the commands from the Makefile and running them yourself. Okay, I'll give like 2 more minutes, then we'll move on. How many people are done yet?
Sorry, I had to download it, so I'm a little behind.
No worries. Yeah, I'll give you a few more.
So so the command is cd documents / CMake training / exercises / section 1.
Yep.
I'll try that.
If you aren't able to get through all the exercises, it's not the end of the world. It's just, these are just kind of to help demonstrate. But it should help you understand what's going on. Okay, 1 more minute.
I'm having an error that says there's no such file with that, or file or directory with that name. Is that
Which command are you running?
the open the terminal to CMake training exercises section 1?
So where did you clone the Git repository?
I don't think I know enough about what I did to tell you, to be completely honest.
Dang, I wish I could go and look at your screen.
Yeah,
We'll
I'm
have to figure
sorry.
things out later.
Yeah, I think I'm going to try and watch a YouTube video to install everything and then watch the first video later. Because I think I'm quite behind right now.
That's okay, you can just stick with the presentation, and you can go back and do the exercise later if you want.
Actually, that works too, yeah.
All right, so that's probably, I think I'll call it there for now. Just wanted to show you guys how you can do this. So if you are able to get it done, you should see this output from the program. This isn't really relevant to this. This is just what it's supposed to print, if you were wondering. So now we'll go over what we actually did with these commands. So the first thing that we did was we compiled each CPP file into an object or .o file. Then we linked all the object files together into an executable. So there's 2 steps involved in this, like I said. The first step is the compile step, right? So in the compile step, the compiler takes the entire source code for a file, including any pound includes it has, and then it generates the equivalent machine code. So if we have movingquadreg.cpp, that goes to movingquadreg.h, and it goes to a header that it includes, like limits. Make sense? So then for a link step, we take multiple .o files, and then we send them through the linker. We send them through G++ in link mode, and then that produces an output file, which is test regression. So what we're going to do with that, and that also, meanwhile, it pulls in libraries from the system, like libc and libstd C++. If you've heard of those are basically libraries that Linux and Mac provide that like help your code run. That's where functions like open and like absolute value and sign and all those sort of standard library functions are implemented in those libraries. They come from there. So I guess now another question a lot of people have a question, which is, why does each CPP have to get compiled into a separate .o file? Why can't you just build all the CPPs at once? So has anyone actually tried that, like on a big project, building a bunch of CPPs at once into a single .o? I see a lot of my 104 students doing it, so I know some of you have tried. Oops. No one tried? All right. So the reason is build speed. So it takes a long time to compile each .cpp file, and the more stuff you put in your .cpp files, the longer it takes. So once you get these massive C++ programs that have like a bunch of template libraries, a million inclusions, then you're starting to wait like 10, 20 seconds for each CPP file. So the nice thing about compiling each one separately is that it means that if you make one change, you only have to rebuild one file instead of rebuilding them all. This is called an incremental build. So it's a lot faster, is the big upshot. But the downside of incremental build is that they require a much more complicated build system. And that is where what we're learning today is going to come in. So I will get into that, but I also want to talk about some of those options that we were passing to the compiler. You're going to see these pop up a lot across these exercises that we're doing. And of course, keep in mind these presentations are in the folder I linked, so you can download them if you need to refer back to these. Probably won't need to for today, but you might at some point. So how many of you have seen these like weird options to G++ and have never really known what they do? Does that describe anyone here? All right. Some of you, all right, cool. Yeah, because you always see these and you're like, what the hell, -wall, -std, huh? So, all right, now I'm going to actually clear up on what some of these do. So wall, of course, enables all the warnings. So your compiler will tell you if there's something it thinks it's suspicious. std C++11, that basically sets the C++ standard. So they keep releasing new versions of C++. The first version was C++ 98, then they released C++ 11, and I think later they went on to 14, 17, and 20, I think. But generally, on almost all compilers implement C++ 11, and yeah, it took until about 2017 until most compilers implemented C++ 11. Compiler writers are behind, man. They are really behind, but they are at least it's getting a little better. Like I think C++ 17 is now reasonably widely implemented, unless you use Windows and on Visual Studio. But so generally, most modern C++ projects will use either C++ 11 or maybe C++ 14. You might see some using C++ 17. That was actually one of the problems when I was writing the CMake build system for The Sims, was that they used C++ 17 features that didn't exist on Visual Studio. So I had to like backport them to older C++. Anyway, -G, that generates debugging information. Basically what that means is, it means that associated with everything in the binary executable, there's also like a thing that says it came from this line in the source file, it's a variable with this name, it's this line of this function. So that means that when you're debugging the code, it can trace certain parts of the code back to where they came from. This is completely useless if you're a computer processor, but it's super useful if you're a debugger like GDB and you're trying to step through the code, or if you're like Valgrind and you're trying to figure out like a backtrace, like I know this happened here in the code, but where did it happen in the source code? So debugging information is used by sorts of diagnostic tools. The downside to debugging information is that it's huge. Like I've seen things that are hundreds of megabytes for a single program built with debugging information on, and they're like less than a megabyte with it off. So you get like 1 to 2 order of magnitude increase in the size from turning debug information on. And then -O0 and -O2, those are controlling optimizations. So basically what that means is whether the compiler will try to find things in your code that could be improved and improve them and make that code run faster. Like potentially if you have a loop, it could unroll that loop into like just repeating the same code a few times to remove the overhead of like the loop jump instructions. That might not make sense, but anyway, so it makes the compiler do a variety of things to make your code run faster. The downside of optimization is optimized code won't step through properly in the debugger. And then also, sometimes with O3, it's optimizations that will make your code larger, whereas with OS, it's optimization that will make your code smaller at the price of making it run slower. Let's see. One more thing, some more common options. If you see -I, that means add this directory to the header search path. So that means when you do #include, that'll search that folder in addition to everything else. I believe -I options are the last option on the compiler command line takes precedence, so it'll search that directory first. Sometimes you can have the same include file in multiple directories, and that is never fun, let me tell you. If you ever see #include_next, run screaming. Don't look at that code for one more second, because that means they have a duplicate header and they've worked around it. It's scary. Okay, and then you see -O, that's telling the compiler what to name the output file that it's writing. So like this works for .o files. .o and -O don't have anything to do with each other. It's -O just specifies the name, so you can use it link step or compile step. Finally, last one to talk about is -D, which you know like C preprocessor macros. -D will define the given macro that you pass it, optionally with a value attached to it. So you can like control C preprocessor macros from the command line. It's pretty convenient, though sometimes it can be misused. We use it in Hamster like to help pass options from the build script into the actual code. So last flag to talk about is the much rumored and much confused -C flag. So if you pass -C, the compiler will always create one .o file from a single source file. If you don't pass -C, the compiler will always create an executable using the files it's given. Sometimes this means it does linking, sometimes it can do linking and compiling, but it'll always at least do linking into a full executable. So if you're trying to compile an object file, you don't want -C. If you are making an object file, you want -C. There are other things you can pass in that you can link that aren't just executables, libraries, static and shared libraries, but we'll cover those in session 2. Okay, so we're making good time. We're now halfway through. We're now through the first part of this, where I just want to go over some of the stuff about compiling C++ code in general. So 2 steps, compilation and linking, and there's a lot of different options that you use to control the compiler. A lot of different options. That list I gave there probably isn't even a fourth of all of the options I've seen for various things. There's a million of them. So and luckily, they're usually at least fairly well documented, so you can look them up. Anyway, now we'll get to the part that I'm sure you've all been waiting for, which is how to actually write a CMakeList.txt. So I'm going to walk you through it. So first of all, why is this presentation about CMake? There's a lot of different build systems available. You may have even heard some bad scandalous things about CMake. Those things are going around, regretfully. So there's a couple good reasons to use CMake. Number one is that it's cross-platform. Basically, it'll work on pretty much any operating system you're trying to run, even like weird supercomputers. That's the thing that they support. FreeBSD, Windows, OS X, Linux, all the common ones, and a lot of the really uncommon ones. It also works for Android cross-compiling, which is really convenient. And it also generates build files for different build tools. So you can run it with Make, you can run it with Ninja, which is like a better version of Make that's smarter about handling multiple cores and runs way faster. You can run it with any number of like IDE-specific build tools. It's very powerful. It's also really convenient for developers, because if you have a project that's described in CMake, you can load it into any number of different IDEs. You can load it into Visual Studio, you can load it into like CLion, you can load it into Xcode, you can load it into KDevelop. Basically, almost all IDEs have some way of loading CMake projects into them. I think Visual Studio Code works too. So it's a lot better than like being locked into one specific IDE, and it gives you full IDE features. It's also really capable. Like there's some build systems out there that are like, oh, we're gonna make your build scripts really simple and easy, and we're gonna do that by removing like half the things it's possible for a build system to do. And those are really convenient right up until you need one of those features and there's no way to implement it. So CMake is really capable. Like you can use custom functions and scripts to do just about anything. It is a Turing complete programming language. Pretty much anything you can do with programming, you can do in CMake, even though it might be a little bit painful sometimes. And also it basically has support for defining your own types of commands and targets. So even if you need to do something other than compiling regular code, you can do that with CMake. Finally, broad community support. CMake is currently the single most popular build system available for most like C++ projects that are being actively developed. So there's a lot of help and a lot of like useful libraries and find modules around so that you can get a lot of support for it on the internet. And also, if you find a random project, there's a good chance it already is using CMake. So there are some CMake haters out there, and I don't completely disagree with them. Sometimes there are things about CMake that are not the best. And these are things that you'll probably hear about criticisms of CMake, and you should be prepared for them. And some of them are a little bit true, some of them not so much. So most common criticism of CMake that I hear, the syntax is weird. This is pretty true. CMake syntax it's a little bit similar to bash scripts, but it's also just really its own thing that it's not immediately related to any other programming language. It has a lot of weird quirks, like escaping semicolons, escaping quotes is a real problem. And it's just kind of limited, and it's very alien to people who've learned like C++ or other programming languages. So that is a legitimate criticism. It also has lots of history. This can be a good thing and it can be a bad thing, but there are a lot of functions that were introduced like 5, 10, even 15 years ago into CMake that have since been deprecated but are still hanging on because they want to preserve backwards compatibility. Seriously, CMake, the most recent version of CMake is backwards compatible at least a decade, like to like CMake 2.8 or something. They're very serious about backwards compatibility, but that does mean they get like cluttered up with old variables and stuff that are no longer really in use. So it's also ugly. Like, this can be true, but it's also ways to fix this. So sometimes if you're trying to make CMake code to do something simple, it can be really verbose, and it can be a little bit obscure, like how do I change this? But there are a lot of ways to prevent this, and a lot of those deal with using custom functions and using custom interface targets, which we will talk about in this presentation series, how to do that effectively to make your code really nice and clean. It's also a little bit esoteric because sometimes, well, there's a lot of common functionality like what does this function do? What is this variable for? Those are generally very well documented. CMake actually has on a whole pretty good documentation, but there are some specific things where like you're trying to do them and you don't have documentation about at a big picture level. Like if I want to make a find module, what do I do? If I want to interface with this library, what do I do? Sometimes that kind of thing is a little bit lacking. We are going to talk about that in this presentation. So now let's talk about how CMake actually works. So CMake is a build system generator. So what it does is it takes a build system, it takes the build files written in CMake language, and those potentially also include other CMake scripts, and then it generates Makefiles. Those Makefiles and then actually contain the build commands, like they do the commands you just did to build all the code. Those are handled by the Makefiles or whatever other thing CMake outputs, because it can output a lot of different things. For these presentations, we are going to be using Make, but just know that this pretty much applies to any build system that CMake supports.
Jamie, what's the difference between Make and CMake?
So Make is a much, yeah, I should explain that. Yeah, Make is a much older program that it's still in somewhat common use to build like relatively simple C++ programs, and it's also a lot more generic. Basically, it's just a way of saying, I have this, I want to build this file, it depends on running this command, and it depends on these other files that are needed to run it. If you've taken 104, you will have seen a little bit of Make type stuff, but in general, it's basically just it's like a rule executor. It says in order to build this file, it needs these other files and this command run. That's basically what you need to know about it. And then it's its own program that you can use it. You can write Makefiles by hand, but that's a lot harder. So CMake makes writing Makefiles by hand a lot easier. So basically, what is a CMakeList.txt? You guys have maybe seen this before. These CMakeList.txt files, they kind of infect every project that's used for CMake, and for good reason. So these are the build files, and these are the things that tell CMake what it's actually supposed to do in this folder. So the top level build file, which is the one in the root folder of your project, has a couple important tasks. It initializes CMake, it sets all the compile options, and it also takes care of inspecting your system and finding libraries that it needs to use. And then the build files in all the subdirectories also handle the code in their respective subdirectories. So that'd be like setting compile options that are specific to that folder, building the code into the actual targets it's supposed to be built into, and then linking the targets into the libraries they depend on. We'll go into a little bit about what specifically a target is in the second lecture, because it's a little bit of a complicated question, but just for now, know that it's like something you want to build, like either an executable or a library. And yes, I know I say executable wrong, but I'm going to say it anyway. So these are just an overview, and we are going to talk about each of these functions in detail over the next couple sessions. So don't be afraid. This is just a random example of CMake syntax that I picked out, but it is at least reasonably representative of what the CMake syntax looks like in general. So there's a lot to go over with CMake syntax. So every line in CMake contains a command or empty space. So command calls will continue across lines until it reaches a closing parenthesis. Can you guys see my mouse cursor?
Yeah, we can see it.
We can't. You can see? All right, yeah. So like this would be one command. So it starts here, it goes up until the closing parentheses. This is also one command, even though there's not a quoted string there. Actually, this is a bad example because it's line wrapped. But this is a command. Like there's a new line here, it continues until this closing parenthesis. And then they have variables. Variables are set using the set command, and they're evaluated using $var. So if you see, or it's dollars curly bracket var uncurly bracket. This is why I say it's kind of like bash scripting, except you have to have the curly brackets, unlike bash. In bash, you don't have to have the curly brackets. In CMake, you do. So white space around the commands is not very significant, but white space between arguments in a command is significant because that's how you separate the arguments. Like if this white space wasn't there, it would be one argument, but because that white space is there, it's two arguments. That's also something that's similar to bash scripting. So then also in CMake, everything is a string. Some of you might be really facepalming right now, but yeah, everything is a string. So including arguments to commands, like example, just as a random example, add compile options here is being called with two string arguments. Everything is a string literal, whether or not it actually has quotes around it. The quotes are used if you want a string literal that has spaces in it, and you don't want that to be considered a bunch of different arguments. So that's always something you got to think about. Do you guys know what I mean when you say string literal, or are you confused? Well, if you haven't heard the term before,
Sorry, I was going to say I was confused.
Yeah, if you haven't heard the term before, basically it refers to something that like text that's interpreted literally as part of as like just text that's interpreted literally as instead of an actual instruction. So like this text here, this find package, that's the name of a command, but everything inside these parentheses is string literals because they're just passed as they're written, and they aren't like turned into anything else. In other languages like C++, MATLAB, etc., you have to have string literals surrounded by quotes. But in CMake, a string literal is any text that isn't explicitly part of something else. Kind of weird, right? But not so weird you can't figure it out. So yeah, variables in CMake, all data is strings. Some variables are lists. Those variables are actually just strings with semicolons separating them. Yeah, I know, kind of lame, right? You are not going to be a happy camper if you need to actually have semicolons in a string and even put that string in a list. It does not work well. So you always have to be a little careful when you need to pass around semicolons. Thankfully, it's pretty rare. I think I've only ran into that like once, ever. And then data is converted from strings to other things like booleans and integers where needed. Like basically if you have an if statement and then you have something in the parentheses, that will then evaluate that. There's some fairly complicated rules about what types of things are truthy and falsy. But for now, let's just say that there's certain strings like true, it's like false, no, off, the number 0, and any string ending in hyphen not found, there is a reason for that. Those are falsy strings. And then truthy strings are any string that is not one of those strings. So that will evaluate to true and put in an if statement. Kind of weird, right? But you get by. So then use a set command to assign a value to a variable. There's a lot of set commands in this. For example, you see like quadreg sources is being set to this, whatever that is. You don't need to know what that is, but you can see that things are being set to stuff. Okay, here's a quick question. What would the variable test regression sources contain once you evaluate it?
Test regression.cpp.
Exactly. And what about quadratic regret sources? Well, that basically follows the same thing, and that is a list containing main.cpp and matplotlibcpp/matplotlibcpp.h. So another weird thing about it is case sensitivity. Function names are not case sensitive. So the thing before the parentheses, that can be capitalized however you want, including SpongeBob case if you want, and it won't care. The convention is that functions are usually lowercase, though you might see some older code that has them uppercase. And then variable names are case sensitive because reasons. So the convention is that variable names are all uppercase. Your shift key pressing finger may get tired when writing CMake. That is a fair warning. Some people like to use lowercase variables to mean local variables, but it's kind of to each their own. I just use all uppercase variables. Variables do have scoping, and it works basically how you would expect. Basically, each directory is its own scope, and also each function call is its own scope. It's actually kind of similar to C, except that like logical blocks don't have, like a for loop doesn't have scope, but functions and directories do have variable scope, and it works how you'd expect.
Wait, Jamie, can you go over like how the lists, like how you set the list to a variable? So
set? That would just be like lines 18 through 20. This is a set command, right? And this set command, seen as a function, is being passed 3 arguments. The first one is quadratic or get sources. The second one is main.cpp. The third one is matplotlib cpp-matplotlib cpp.h. So what this set function does is, first of all, it'll get these arguments and it'll concatenate them into a semicolon separated string, and then it will set the first argument as a variable with that data.
What exactly is the variable in this case? I'm still kind of confused.
The variable is quadratic or get sources.
Okay, and it always has to be in the format of caps with the underscores, correct?
Yeah, variables have to be one word. They don't have to be caps, but they're caps by convention.
Okay.
So as in, people look at you weirdly if you don't use caps. At least people who are in the know about CMake. Maybe. Or maybe they won't care. But they might. Anyway, so CMake commands, if you've used Python commands with keyword, so basically CMake commands have 2 different types of commands, keyword arguments and positional. So if you've used Python, you might have known what I'm talking about with keyword arguments, where basically you have like a function, and then there's a name, and then that name is set with an equal sign to other arguments. So CMake things work similarly to that, where basically you have a keyword, like in this case it would be components, and then that's set to specific arguments, interpreter, development, numpy. Those are the arguments that are passed for that keyword. And then other functions use positional arguments, where basically you just know that the first argument to this function is one thing, the second argument is something else, the third argument is something else. And no, there's not a very good standard like of which types of functions use which types of arguments. You are always going to be checking the documentation about this to see how to do that. So it can be a little annoying, but it's straightforward once you get used to it. It's always good to look at the documentation so that you know what kind of arguments this function takes. I've been coding CMake for years. Whenever I'm writing CMake, I have at least 3 tabs open to the CMake documentation, checking function arguments and signatures. So you can never remember unless it's like you do the same function like every single day.
Jamie, are keywords also string literals because they're in orange instead of like white?
Yeah, that's actually, yeah. It's really funky how that's implemented. They're kind of both string literals and they aren't. Like, they always have to be the same, but as far as the language is concerned, they're a string literal. As far as this syntax highlighting is concerned, basically the Sublime text thing just has like a list of keyword arguments that it knows about, and it colors those orange. There isn't any sort of other way you can figure it out. From a language perspective, they're the same. And it's up to the function you're calling to actually go through that. So fun fact, under the hood, every CMake function just takes a list of arguments. And then there's another function you can call inside a function that will then go through that list and then parse out the keyword arguments. It's really weird. And I can't believe they weren't able to come up with something better than that, but that's what you got to do. It's called CMake parse arguments. I'll probably give a demonstration of it in a later section of how to write your own custom function. It's one of the more annoying things about CMake, for sure, is using CMake parse arguments. We will go into custom functions later. So, CMake directory structure. Unlike Make, CMake makes it really straightforward to keep your compiled files separate from your source directory. Like, if you were in 104 and you used Makefiles, you might have always noticed that you always had trouble with junk files, right? Where you'd end up with a lot of .o files, executables, yada, 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 all that junk in the same directory where all your code was. And if you weren't careful with your make clean, you might accidentally delete something you cared about when you're deleting all those files. That happened to a couple 104 students this semester. They accidentally had rm./star in their make clean, and it deleted everything. And we couldn't help them get it back because they hadn't committed. But other than that, it's also just annoying because it clutters up your directory, and you keep having to use git ignore. You keep having to use you keep having to deal with all these extra files. So CMake by default will store your binary files in another folder without you really doing anything. So there's 3 directories to keep in mind with CMake. There's the source directory, which is where your code is at. There's the binary directory, which is where all the intermediary files like .o files, executables are at. And then finally, the installer, which is when the build is done, all the final products of the build will get copied there. So that would be like /usr/usr/local, C program files if you're on Windows, that kind of thing. So when you're running CMake on the command line, you're always going to cd into the binary directory, and then you're going to pass CMake the path to the source directory. So directory variables.
Oh, one quick question. It was back one slide, so I didn't get to ask it before. There's one line where there's just a lone period on line 27. What is that doing there?
Private period? Your question?
Yeah, or just like what is the period?
Oh, the period is just a literal for the current directory. It doesn't have any special significance.
Oh, I see. Okay.
So yeah.
Okay, thanks.
That's actually something I should go into, which is paths and CMakeLists are always interpreted relative to the source directory. So if you need to refer to something in the binary directory, you should use CMake binary dir. So there's specific variables that will access these directories. I have a little example of what that would look like in our setup. So let's say you create session 1 build and then run CMake there. Then your thing would look like this. CMake source dir would point to session 1. CMake current source dir would point to quadreg, which is the current CMakeList.txt. Oh wait, yeah, that would be for this CMakeList.txt. And then CMake, I actually think this doesn't match how I set it up, but this is if you had a subs directory CMakeLists in quadreg, it would have these values. I don't remember if that actually exists or not. But anyway, so CMake source dir points to the top level source directory. CMake current source dir points to the source directory you're currently in. CMake binary dir points to the top level binary dir, and I'm sure you get the pattern for CMake current binary dir. CMake install prefix is a little different because that's one that you can set, and it isn't immediately like obvious what it would be. But the sort of default value on Linux is user local. That's just where it'll install stuff.
Wait, Jamie, can you explain that again? It's a bit confusing. How do you determine like what it is relative to?
For which variable?
Like for all of them. Like
so all of the current directory ones, those are relative to the current CMakeList.txt. So basically, CMake creates like a mirror of your directory structure. Let's see. Did I actually set it up like this in the real thing? Man, it would suck if I forgot to do it like that.
You did.
Okay, yeah. Oh no, no, it is a bit different. So basically, this would be if you had a CMakeList.txt in quadreg, then for that CMakeList.txt, it would have the current directories would refer to the quadreg subfolder. But then you have the non-current ones that always refer to the top level directory. That makes sense?
wait, so why is CMake source dir pointing to session 1 and not quadreg?
Because CMake source dir always points to the top level directory.
So how does it know which one the top level directory is?
That is the directory with the top level CMakeList.txt. So basically you have a top level CMakeList.txt that sets up the build system and that includes the other CMakeList.txt. You can't run a subdir CMakeLists as a top level CMakeLists usually.
Okay.
And so you have one that's designated as the top level. So, and then the way you actually, I'll go into that maybe a little more later, but the way you'd actually do that would be by setting that up. It would be by setting up your CMake command line. And that will, the way you, the command line you invoke CMakeLists.text with actually determines what those directories will be set to. Usually there's only one possible one that will work. So yeah, hopefully you'll see what that means a little bit later. So now we're actually going to do a second exercise. So we are now going to do simple CMakeList.text, and you want to, let's see. So what you're going to do is go into your session 1 folder, and then make a new CMakeList.text, and you're going to open it in your text editor.
Jamie, going back to the cloning part, like apparently, like I actually just cloned it to my regular Windows desktop. How would I actually clone it to the WS?
Actually, you know, I realized I think it might actually work better. Hey, I'll share my whole screen just a sec.
You can get to WSL, or sorry, to your Windows portion from WSL by cding to /mnt/c/rest of the path.
Perfect. That was exactly what I was going to explain. Okay, I hope it's still recording. Anyway, you guys can see my screen, right?
Yep.
Okay, cool. So let's see. I'll actually do a little example of that because I actually. Oh wait. Okay. I'm gonna have to use it through my 104 VM. So I don't actually have WSL on this computer. Forgot. I've also got to clone the thing. Geez, I didn't do this setup and I was yelling at you guys. What am I doing? Let's see. I'll just get that cloned real quick. So it would be let's see. So it would be git clone, and then I'm gonna paste in that path. Oh, I didn't copy, I guess. That's gonna clone in, and then exercises session 1. Also gonna open up Sublime Text to this folder. So then, you can see that that's going, go away, is that we're gonna make a new folder, a new file in here called CMakeList.text. So what is that file gonna have in it? So the very first thing that's gonna have is the initialization code. So all CMake programs always need to start with these 2 lines. You always need these 2 lines to get your program going. The top level, this only needs to be in the top level file, but it won't really start without these 2 lines in there. So the first thing you're gonna do is CMake minimum required. I believe that the 104 VMs have CMake 3.5, so I decided to go with CMake 3.5. Backwards compatibility can be a big issue in CMake. 3.5. So basically what this does is it disables backwards compatibility for versions older than 3.5, and it will show you an error if you have your if you have an older version and it tries to load this file. So it's fairly smart about it. Should be thankful that it's like it's pretty good about this usually, because it can get really annoying in certain build tools and situations. The next thing we're going to add in is we're going to add a project statement. So what that's going to do is it's going to tell CMake this is a project named test quadreg and that it uses these languages. That will tell it to search for a C and a C++ compiler. Actually, wait, I think we'll need a C++ compiler for this, right? Yeah, we only need a C++. You can also put other language in there like CUDA, Fortran, C#. It'll try to find compilers for all of those. But I will say using CMake for anything other than C, C++, or Fortran is a little bit experimental. Oh, and CUDA. Those are the top 4 languages that are actually like well supported. You can even do Java if you really want to, but it's a little bit janky. I think I used it once and it worked okay. Anyway, so these are the 2 languages these are the 2 lines you're going to need at the start. Everyone got those?
Yeah. Quick question. How did you get Sublime Text to detect that it is a CMake file?
Good question. You should look at your, let's see, I think I actually posted a link to this in the avionics in the repository link. If you go there and look at the README, It's the CMake package for Sublime. It's a little bit of a pain to install, so, well, it's not too bad.
Cool.
So do you have
I'll take a
package
look at it
control for
later.
Sublime installed yet?
Should
I'm
work
not
without
sure.
it. It'll just be annoying.
Yeah, it'll work fine. We'll go through installing it later. It is it's really nice syntax highlighting. It's actually better than what CLine has. That's an IDE based around CMake. So I guess you know what their priorities are. She's. But anyway, everyone else have this? Everyone good? Speak now or forever hold your peace. Oh yeah. Also, C++ is called CXX in CMake. And the reason for that is probably so it can be used as a valid file path, because most operating systems don't allow plus signs in file and folder names. So clearly the C++ designers were not thinking ahead in that particular aspect, even though they were really thinking ahead about everything else. Jeez. So now we're going to list our sources. So this is going to have the source. This is going to have the files that we need to put in our build file. That's going to have testregression.cpp. And it's going to have moving quadreg.cpp. There we go. So this is pretty straightforward. You guys know what this is doing, right? I talked about it earlier. Anyone hazard a guess?
You're setting a variable.
Exactly. Perfect. So what this is doing is it's setting test quadreg sources to these two variables in it. So then our next thing is compile flags. So we're going to start adding some compile flags to these. So we're going to include directories quadreg. It's going to include directories quadreg. Oops. Anyone guess what compile flag this is going to turn out to add later? Because this tells CMake that that quadreg directory that needs to be included in our header search path. So like if we so that test regression.cpp, this does pound include moving quadreg. In order for that include to resolve correctly, it needs to be able to know that this folder is also on the include path. So that's what this include directories is doing. The next thing that we need is adding compile options. I'll just put in wall in there too, so we have some nice warnings. Always good. So what this is going to do is it takes a bunch of string arguments, and then it just passes those straight to the compiler. Something else to know about these functions is that these are both directory scope functions, which mean that they affect the current directory and every subdirectory of the current directory. So there are many other ways to set that up. You can associate compile flags with specific targets, or you can associate them with the entire project regardless of the current directory. We will go into those next time, how to do serious amounts of compile flags. For now, that'll have to do. So and then lastly, we need to create our executable. We are almost already done with this CMakeLists. And then this is going to take some sources, which we're just going to take this variable, and we're going to evaluate this variable. There we go. So now we've got test regression, and that is being built from test quadreg sources. So now we are actually ready to run this build system. So what I'm going to do here, I'll clear all that junk out that you don't care about, which is so now we're in session 1. So now what we're going to do is, this is like the basic thing for running any CMake build system, which is we're going to make a build directory. That build directory can be a subdirectory of your thing, or it can be anywhere else on your system that you want. I always like to make it a subdirectory. So we're going to make dir build, cd build, and now we are going to actually run CMake. So that is going to, oh, whoops, executable, jeez. There we go. So that is going to run CMake. It's going to find a C++ compiler. It's going to make sure it's going to run some checks on it. Those are useful because later you can reference like information about the compiler. And then it's going to generate some build files. So if we look in our build directory, we will see that it has created a couple different files. We have CMake cache.txt, which we'll get into in the next session. We have CMake files that contains a bunch of internal stuff. We have the install script that we don't really care about, and we have a make file. Now, if we look at this make file, it's a little bit complicated. Here, I can pull it up in Sublime. This is the make file that CMake generated. It is a lot of stuff, even for a relatively simple project. But what it is very capable. So if we do make help, we can see all the stuff that it can build for us here. So in this case, we've only added one executable, test regression, so that'll be the only thing here. But there are also a couple other targets that we can use. And a lot of those have to do with the cache that we'll talk about later. But for now, I'm just going to do make test regression. And what that's going to do is build it. And will it work? There we go. Boom. All tested. So if you guys want to see that again, we can, if I make clean, and then if I make verbose, so if I set that option, now it will show us all the commands it's running when it's running make. And look, we have C++ compiler -i quadreg -std equals C++11 -wall. Those options came from here, the include directories and add compile options. And then we had and then we can see that we had -o, moving quadreg.cpp.o. CMake automatically decides what to create that. And then it also outputs moving, and then -c, and then input file, which is the CPP. This is exactly the same as the command we ran earlier on by ourselves. It's just that CMake generated this command for us. Cool, right? I'll show you something else useful that CMake does. So suppose we have a big header here. So this header would look like, so we have this moving quadreg header. Now, normally, if you were using Makefiles, header dependencies are a huge problem because anytime you modify a header, you have to normally like list out like this CPP depends on these 5 headers, and if a header depends on other headers, then oh boy, you got trouble because then you have to like manually track this arbitrarily deep header dependency nightmare. CMake will do that for you because it's actually smart enough to parse the C++ files and determine what headers they need without you having to do it yourself. So like, if I change a character in that header, save it, now if I run make, it's smart enough to know that everything that includes that header needs to be rebuilt. It'll do that automatically. Is that awesome or what? I think it's pretty awesome. So that is actually pretty much it for today's presentation. We just wanted to go through like the basics of building C++ and then the basics of writing a simple CMakeLists.txt. I hope that was interesting, and if you guys want to hear more about that, like how to do, we have our next lecture will be on more advanced CMake, which is going to be on like how to do different types of compile option targets, how to do different compile options, how to use some weirder types of CMake functions, and like how to make code so that you can export it and use it in another build system. Like so you can make a library that you can use in multiple other different places. Then the next session after that is going to be talking about shared libraries, which is one of the most interesting topics about this. We're going to talk about how like all the system libraries work and like how you can have a .so library that's used by a bunch of different applications, has a bunch of shared code, and has its own dependencies. Basically how you can make your application into a library that other applications can easily use. And also going to be some good clues on how to debug the horrifying errors that the shared library system can sometimes produce, which is I'm sure what you're all here for, right? So in this part, so in this part of this, we just talked about basic CMake syntax, and then also directory structure, which is always important to remember. You can't ignore it. It's really important to remember how that works. And then how to do basic CMakeLists.txt. Any questions?
Could you pull up your CMakeLists.txt document again?
Sure.
Thank you.
It's also actually, if you look in the thing, I believe it's in there's a solutions folder in the thing I sent out. Yeah, if you go solutions, session 1,
I see it there.
exercise 2, CMakeList.txt, that'll have basically just what I typed in here.
Wait, Jamie, what is .cpp again?
That is the file extension for C++ code.
So what does it do? Like, what is its purpose?
CPP file, what is your purpose? A CPP file's purpose is the prime directive of having code contained in it that is then executed to do stuff. All C++ code is written in CPP files. So like we can see, this one's got a main function in it, and then that just calls other functions. So pretty much all useful C++ code is written in CPP files, and then also potentially .h files that are used by those CPP files. It's a little hard to explain more into this if you haven't taken like E155 or CS103, but hopefully that'll at least give you the background for what's going on.
Okay, so basically it's a type of file.
Yep, it's basically this type of file. Any other questions?
I have a request. Would you care to explain, or Jay, would you care to explain the yeet not found confound?
Yeah.
So, yeah. Go ahead, Jay.
So CMake apparently has a wide variety of what it considers truthy and falsy. So anything that is not falsy is truthy, and since the word yeet is not falsy, we can use it as a truthy statement. So if we'd like to enable a certain flag, we can go -d use extend, for example, equals yeet. And if we want to disable extend, we can do -d use extend equals yeet not found.
I think we used it on the Poise launch setup the night before. That was our official radio setting for Poise launch. It was fun times. Let's see. Any other questions about CMake?
Yeah, I'm getting an error when I'm trying to run CMake, but should I stay after for that? It's cannot determine linked language for target test regression. Cannot determine.
Is it possible you don't have any? Is it possible you typoed your source file list? That's a pretty common thing.
Okay.
Or maybe you had your. Maybe you added a .h file, but not any of the CPPs. Adding CMake files, adding .h's to the sources for an executable can be a little confusing. Because normally you might think adding .h's to a source file, everyone always told me that's a horrible thing to do with Makefiles. And it is bad to do with Makefiles. CMake doesn't care. It notices the .h extension, then it just gets rid of the file. What does care is IDEs like CLion. Those actually need .h's to be added to the source file list so that they can associate them with a specific target that they're used for, and like show them as built in the IDE. So if you want to have your good support for IDEs, it's actually good practice to add .h files. Even though a lot of other people will say you shouldn't do that, the final word on it is to do add them. Which I didn't do here because we're not going to use this in an IDE. But
is there some equivalent to make clean for CMake?
Yeah, there's two levels of clean. So all right, so CMake generates Makefiles that actually just support make clean. So you can just do make clean. And if you'll see, that has deleted all of the .o files, but it hasn't deleted any of the files that CMake generates. So a very common problem in CMake is that CMake is very persnickety about where its build directory is located. So like, let's say I'm going to take this build directory and I'm going to copy it from session 1 up to the exercises folder. So it's next to session 1. So now I'm going to cd into that, and I'm going to run the same thing. CMake CMake, and then //session1. And it's going to say, this current CMake cache directory is different from the directory where things were being built. I'm not going to do anything. So to deal with that, you just have to Control-A, delete everything in the build directory. There's no other way to deal with that. That is one of the most common stumbling blocks for CMake people, is they move the build directory and then suddenly it's an error and you don't know how to fix it. We got a lot of that in 104. The test case and stuff. Did I answer your question?
Yeah, that solves the problem I was running into.
I'm always going to need to be doing like rm dash. I have rm alias to rm rf. So if I do rm star, it'll do are you sure you want to delete all the files? I think my ZSH is getting very suspicious about me. because of all these CMake build systems that need to be hard cleaned. Generally, to do that, you have to at least delete CMake files and CMake cache. That's what you need to do to do it like a hard clean. The other files can stay or go. That also happens if you install a newer version of CMake on your machine, so be careful of updates, because it'll make all the build directories you've configured not work anymore. Looks at Homebrew angrily. When this happened to me a while ago.
Jamie, how is that you have like the current like setup on your computer? Like, how did you get the, I guess, the workstation to show up with like the Google Chrome, Mozilla, and all that?
This is a virtual machine. We installed this as part of CS 104. So basically, I'm running Linux inside my I'm running Linux inside my Windows machine. It's a bit of a pain to set up, so that's why I advised you guys to use WSL. Is it's a lot lighter weight to download and use.
Okay, I thought we were supposed to be seeing the whole thing right there. Okay, got it.
Yeah, I would have used WSL, but I forgot I didn't have it installed on this computer.
Got it. Cool.
Okay, any other questions? Is there anything specific that you guys? Oh, sorry, question?
Oh, sorry. Like, what was the command that you were using to like list all the things that CMake or
Make
all
help.
the make? Oh, make help. Okay.
That's a pretty common command to run with the hamster build system. Oh wait, it's not configured. That's a pretty common command to run with the hamster build system too. Is make help, so you can remember all the target names because there are a lot of them.
Ah, all right. Cool. Thanks.
Let's see. Also, is there anything that anyone wants me to cover specifically? I know Mark talked about wanting me to cover how to integrate with Python for the new Sims build system. Is there anything else?
Can you explain how header files work in detail, and like how you can have code in header files and still like compile it without including it and stuff like that?
Sure. Okay, so this is a bit complicated, but we'll do what we can. So if you haven't seen before, basically all C++ code is split into two parts: the header files and the CVP files. The header files are basically where classes and function prototypes are defined. So this basically is what tells, I'm sure you've seen this before, just as a general background. This is basically what tells the compiler in moving quadreg.cpp, these things exist. So this is telling it like a light, easy to digest format that doesn't require a lot of time to crunch. It's all the like pre-definition. So then what happens is other like test regression.cpp includes moving quadreg.h. The actual pound include is literally just take this file, copy it, and then paste it at the top of this file to replace the include statement. It's just a textual copy and paste. So then before it will build anything in this, it first sees this header, which has all these forward declarations that says like, this is the stuff that will exist in some other file. So the goal of headers is to have all these forward declarations, and the goal of pound include is to work as a copy paste that will take the header and then put it at the top of this. So of course, if you change a header, that means that the total contents of the source file have changed. So you should rebuild the source file. But this is something that a lot of people don't have. That like if your build system requires you to specify that manually, it's a huge pain to figure out.
How's that you? So how do you clone the, I guess, the file that you had on your GitHub to the WSL? Like I figured out how to do it to my Windows, but like I wasn't sure how to do it specifically to the WSL. Like I saw you put like the CD into documents, but I keep getting no file/directory when I try to do that. So
oh well, the file on your system is different. So it would be so it'd be wherever you cloned it. It's hard to know what specifically it should be without being able to see your system.
Okay, because I guess I'm trying to figure out like how to get rid of the no such file directory, like because when I did the pwd command and I just got like /home/
I would need to see your system, Diego. How about let's talk after?
Okay.
All right. Anything else? I think that brings this presentation to a close. So thanks for coming, everyone. Hope you learned something, and we'll have part 2 in probably about 2 weeks or so. So see you guys around.